Okay, thank you. Okay, let's get started. So last time we talked about two issues. So one anomaly. We talk about one anomaly. So one is due to curved worldsheet. The curved worldsheet. Worldsheet PAA is equal to C over 12 R2. This is the curvature of worldsheet. One problem is this one. And then one student asked me to do, oh, by the way, so lecture notes is again updated, so you should take a look at the e-learning. I just keep updating till last moment, so you should take a look at the updated one. So one student asked me about how to derive below curved work. So the component vortex identity in curved background is some bar. Oh, sorry. Last time I just drew like this way, 2 pi. Anyway, so the component, let's see, E plus, so I received a question. I mean, if you have a question, just tell me. I mean, it's quite amazing. It seems like so far you guys do not ask questions simply you understand something. I mean, in string theory, you have to make your hand dirty, otherwise you don't understand anything. Okay, so, times, So this is the at the beginning of component word identity. So this is current for component symmetry. As I mentioned, so the current for component symmetry is like this way, whatever. See? And then in curved background, let's see. So this is the conservation of the data current, but in quantum version you need to consider insert you need to consider operator formalism in path integral. Okay. And from here, I mean, so GZZ, G is now DZZ bar. So from using here, here what you get is 2 pi, and that's what's written in the lecture note. What's written in lecture note? And then times operator. So that's what's written in lecture note. And from here, I just wrote down this is equal to in lecture note. And then students ask what's the derivation from here to here. I'm not sure you guys just follow each step in the lecture note or Bosonic. I mean, when you're a student, you should do. If you want to learn something. Yeah, also when I was a student, I also derived. Yeah. and also the equation in the Polchinski. Anyway. So the question is from one to the other. So the main question is that since so this guy see this one. Do you understand? So as I mentioned, so delta z epsilon t. The question is tz, which is equal to partial minus 2 del omega. I just use small omega now in the lecture note. So this nabla z is del minus, so this is the Christoffel symbol, and acts on EZ and TZ. And since homomorphic derivative C E of Z, so the question is how this action can ignore from one to, when you go from one to the other. So that's a question. But indeed, this plus, this TZZ. So, sorry, this is TZZ. What I meant is TZZ. Sorry, TZZ. Okay. Note that TZZ is no longer holomorphic in curved background. TZZ is what's written upstairs. Partial omega. The omega to omega plus TZ. Okay, that's what's happening. And then note that you can just act two quantity. So T, I'm making some mistake. You should correct me. This is TZ bar. That's why you guys are got confused. Yeah, TZ bar. Okay. And then this is T. Yeah. So TZ bar, TZZ is this one. So it's irrelevant. So I don't need to write down. Sorry. Make you confused. So you should correct me. Note that so TZ and also Z bar, that's the same quantity, is indeed, if you, so this one is equal to 0, okay? And then, but if you, this one can act on E of Z, but if you combine them together, note that the, so the last time I just derived the following long time ago in the conformal word identity. What was it? Let's, yeah. So partial mu del mu j mu is equal to 1/2 t mu del mu epsilon mu plus del mu epsilon mu. Okay. And by using so therefore so we need to treat this quantity to be 0. So this is symmetric. So therefore what's acting EZ epsilon, so this is EZ plus delta Z bar epsilon Z bar TZZ Z bar has to be equal to 0. Okay. So when this one acts on 0, okay. So this is current conservation. So therefore this, so of course this one sees epsilon 0, okay, epsilon Z, so it's because it's holomorphic, and also this one is anti-holomorphic dependence, but once you add them together, you can ignore times TZZ, so TZZ bar is equal to 0 due to net current. So therefore, the action on homomorphic derivative on epsilon of Z cancel with anti-homomorphic derivative on E of Z bar. So therefore, you can ignore. And at the end of the day, so you can ignore the action on the homomorphic derivative on epsilon Z and the anti-homomorphic derivative on the here by they cancel each other. And at the end of the day, you can bring it to this. That's one remark I should make. Okay. And another thing, so we talk about is the curve target, target space curve. Target. So manifold and D, 1 comma D, minus 1, G mu. Curve target. So so we talk about curve target, and what we notice that if you scale the energy scale, there's a quantum effect, so that we need to take into account the dependence, the scale of the quantum due to the quantum effect. That can be seen at the beta function. And at the end of the day, so what we saw is 1 to alpha prime. So, sorry, maybe I should write down the action. S is equal to 4, 5 alpha prime, d squared x, x mu, g mu. Okay. A. So that's the action we consider. And then, so TAA is somehow proportional to beta function of this G mu. The series no, so this is a nonlinear sigma model, nonlinear sigma model, and it's no longer a free theory, so therefore you need to consider the quantum effect. To do that, we just do some cultivation theory. So we just first perturb this action, this G mu of x is some, you just consider the perturbation at some point, the metric at some point. So then the leading term is proportional to Riemannian curvature. And then do the perturbation theory. So that's what we have tried to do last time. And then, so for instance, yeah, so x mu is somehow if you do the momentum space, so it's heuristic, but can be written like this by IK, transformation, and leading term is G mu, but the first one term is R mu. And times loop correction. So times, so one is called so log divergence. Another can be the Kodak divergence. And this is, so if you consider x mu, x1, x2, so this we need to consider the one loop term, the presence of this this perturbation, this leading order correction. Okay. Leading order correction, and this is log divergence, and this quadratic divergence. And then we will get rid of this infinity or divergence by using this usual dimensional regularization or putting counter terms. Okay? And this quadratic, just be heuristic, can be cancelled by counter term. This cancel by counter term. whereas this will contribute to beta function. Contributes to beta function. So that's what we're going to see. To see that again, I mean that's what you have you will learn in QFT2. That you just define some bare action as bare and as physical and plus S counterterm. And then do the wave function renormalization, just use your renormalization. Okay, so the bare. So let's consider the bare. So this S hat bare is S hat, the X hat, and G hat. And do the cultivation theory, usual wave. So you consider wave function renormalization. And also, where the wave function renormalization G mu, delta mu, plus sum over. So you just have cultivation theory on this wave function renormalization. So G hat, also mu nu, is just perturbed by coupling constant. Let's use upstairs because upstairs lambda over E. So of course lambda here is the lambda is a scalar pair, and this is E is physical scale. And so on. Then, so this 2-point function can be written in terms of so this is one loop correction, and also there's some contribution come from counter term. So this is a bit heuristic, but I mean, if you try to derive everything, it takes a lot of time. So you can just refer to this column and CT. I already forgot the reference name. What was the reference name? CT89. So you can just take a look at the derivation. So there's a contribution coming from counter term, which is this mu and plus Z mu 1 plus Z mu. So this wave, this Z is called wave function renormalization. This is called wave function renormalization. And also this is just perturbation of the metric. So, and so this is the leading order contribution quantum effect. And then to determine this one, you need to compute 4-point function to determine ratio and so on, but I just give you an answer. So usual log dependence coming from loop diagram. So you have to do the honest computation if you try to derive. And then if you combine, I think I need a, okay, it's okay. I think, yeah, so it's okay. So if you combine these, if you plug into this effect into here, so what you obtain is that this beta function of G mu nu, which is log derivative with respect to epsilon on G mu nu epsilon lambda is equal to, so let me do the calculation. So at the end of the day, if you plug into here, so this is 1 minus 2/3. Is it correct? I think 1 minus 2/3, and alpha prime is here. What I want is, I'm sorry?
Minus 1 minus, so you can cancel.
So that's what I don't want to have. So I think something wrong in this computation. Sorry. It should be minus alpha. I should obtain minus alpha prime.
Minus alpha prime from the alpha prime G mu.
Alpha prime G mu.
And the last two terms cancel with.
Oh, I see. Okay. Thank you very much. Yeah. So this alpha G mu. So this log dependence really come from here. They come from here. Okay. So that's just alpha prime R mu nu log lambda over epsilon, and the counter term cancel with this one. Yeah. Thank you very much. Thank you very much. Then what you get is alpha prime R mu nu. So that's I missed last time the derivation. So the last time I forgot about including this counter term to get the correct coefficient here. Yeah. And the one half helps me. Thank you very much. Even at this moment. So this beta function. So the essential point is that if you do the loop integral, so it's, of course you have to be careful coefficient. What essential point is that if you do the perturbation of G mu nu, leading term is really Ricci tensor. No, Riemann curvature. And then if you do loop integral, so leading term is always depends on Ricci tensor R mu nu. Depending on, you have to be careful of the coefficient. And this R mu nu really contributes to the beta function. That's the essence of this this loop correction. And in order for the zero to be wild anomaly, free from wild anomaly, so it has to be zero to be. So this has to be zero for theory to be free from wild anomaly. So therefore, the target space for Ricci curvature has to be zero. R mu nu has to be zero for bosonic string theory. So this is the essence. So the target space has to have the Ricci tensor to be zero. So it's called Ricci flat. And this is also true for superstring. I already included superstring at the lecture note in the last. It's also the same for superstring. So bosonic string D has to be 26, and superstring the dimension has to be what? 10. And this is usually decomposed by with 6 plus 4. 4 is a space-time direction, and 6 is so-called internal manifold, and 6-dimensional Ricci flat manifold. And if it is complex, so this is leads to Calabi-Yau 3-4. It's called Calabi-Yau 3-4. 3 means the complex 3-dimensional. So that's what Yau is the main contribution, the first contribution to this string theory. That's why he's interested in string theory. That's one of the main reason, I guess. Okay. So that's the requirement in order for the theory to be free from wild anomaly. Okay. Thank you very much for the help, and then move on. Okay, so we only consider the target space. It has this action so far. Okay, we just changed the first. We consider the flat space R1 minus 1 eta mu nu, and it goes to here. Okay. So we slightly want to generalize a bit more. Okay, a bit more. A bit more. So we already know that what are the massless mode in bosonic string? Do you remember? What are the massless mode, massless states in bosonic string? Okay. Yeah, what are those? Do you remember? So we just act. So this is the first excited state, which gives us like which decomposes 3 irreducible representation as little group SO24. Do you remember what are the massless states? It's very important in string theory. Do you remember? Graviton, good. Graviton. Another. This is symmetric part. What is the anti-symmetric part? B field. Okay, B field. And dilaton. Okay, so this is anti-symmetric part and dilaton. And we want to write down the action by using. So far we only use this G mu nu graviton to write down the action. Okay. So this is target space graviton. Okay. So the reason why the string series catch a lot of attention, so you can quantize this graviton. So you already have graviton, like at least the canonical quantization graviton mode. Okay. So the most general action one can write down is as follows. By using this massless mode is 4 pi alpha prime. And then, so this is anti-symmetric. Instead of using this is G mu nu, we should use, no, HAB, we should use HAB, partial A x mu, partial B x mu, B mu. Okay. So the reason why you use epsilon instead of H is because B mu nu is anti-symmetric. So you have to, when you swap mu and nu, you have to compensate by minus sign for the epsilon. Okay, and then so where are we heading? And then also, so the dilaton part is alpha prime square H R2 phi x. So this is the most general action one can write down. One can write down this by using massless states in string theory. So
you missed an I in second term.
Oh, thank you very much. So I. Okay, so this is the most general term one can write down for by using massless states. So this is the action for the Riemann surface is mapped to the d 1, d minus 1 dimensional manifold. So this is the most general nonlinear sigma model action for nonlinear sigma model of nonlinear sigma model. Okay, and then of course B field is generalization of this is two form. Two form means the you can just have B mu nu. So B2 is dx mu, which dx mu. And it's a generalization of the gauge field in the Yang-Mills or whatever Maxwell theory. It's abelian, so it's a generalization of the some connection or gauge potential A mu. So therefore, its a field strength is just a H3 form, and which is defined by like this way. Okay. Of course, as you. So this is the generalization of F2, the Maxwell field. Okay. So therefore, there is a gauge. So this is physical quantity. And there is a gauge redundancy that of course, you can always add B2 goes to B2 plus D lambda 1. Okay. So this is the gauge transformation one can take. Yep. That's how this B field behave in this sigma model. And the phi just get dilaton. So this phi is a dilaton of a scalar field, and this will play a very important role in string theory. So I will tell you in a minute. Okay. So, and I just give you the result. So this is a hard calculation done by late 80s as far as I know, late 80s in string theory. So one can also compute. So again, so you receive some quantum correction each massless mode. There is no color. So they receive quantum correction, so that you have to consider the beta function again. So TAA is receive this proportion of the beta function. I've already become lazy. Oh, there's a typo in the lecture note. Plus I to alpha prime beta dv nu epsilon AB partial A. So you have to consider all the perturbation theory for this massless mode. And then contribution, like explicit calculation written in the first leading order contribution at alpha prime is written in lecture note. I'm not going to write down everything. And then those, so in order for the series to be free from one anomaly or well defined, so this beta function has to be 0. And this condition is equivalent to taking the following space-time effective action. So this is worldsheet action. This is a worldsheet action. So it's a two-dimensional integral. So it's a worldsheet action. But this condition is equivalent to, so this condition is equivalent to the equation of motion of the space-time. This is space-time action of the following dx minus g e to the minus 2 alpha alpha, and you have the cosmological constant, but this is becomes 0 at d is equal to 26, and then r minus 1 half h wedge star h, and then plus d phi wedge star plus all the alpha primes. So this is the space-time action, as you can see. So this is d-dimensional integral. It's a space-time action. Okay. And if you take equation motion for this space-time action, that's equivalent to beta function vanishes. So therefore, so there is a one-to-one correspondence between this worldsheet action and the space-time action. So the physics has to be the same when you look at the space from space-time viewpoint or worldsheet viewpoint. That's what it means. So you should get the same physics from this action and also this action when you quantize. And also, so from here, so in a lecture note, I already write down the explicit expression for beta function. So beta function of phi to be 0, again, d has to be 26. That's the condition you will get from beta function. So this one is the same as the equation motion of this space-time action. Yeah. So this I didn't write down indices. This one is Hodge star, and then if you take differential geometry course, you understand how to write them down in terms of indices in the physicist way. Okay, so that's the one important thing you can learn coming from beta function analysis of beta function. So you just have the worldsheet viewpoint and space-time viewpoint. And another thing, which is very important in string theory, is that, so as I mentioned last time, no, at the beginning of the lecture, alpha prime is the only parameter that appear in string theory. So I already forgot how many parameters standard model has, but there are lots of parameters standard model has. One has to fine tune to, for the human being to live. But here, string theory, you have only one parameter, which you call alpha prime, and then the rest of the quantity is derived from the first principle. In particular, if you look at this part, if you look at this part, and perform the integral, for instance, so this S dilaton, which is 1 over 4 pi alpha, and d squared x alpha prime h r2 phi of x. Okay. So then, if you assume phi to be the constant, so you just take, if you consider phi as the takes the expectation value, so then what you will get is phi times 1 over 4 pi alpha prime times d squared x h r2. So this quantity is well known to be topological invariant. Yesterday I teach the Gauss-Bonnet theorem. This is exactly what Gauss-Bonnet tells us. So this will give you, so this is the integral over worldsheet sigma, and this will give you oral characteristic of the worldsheet. I think there are lots of mistake in the actually. coefficient in my lecture note. I need to correct it. Okay. So suppose let's suppose phi takes expectation value, which is phi alpha prime times phi. Okay. Then alpha prime cancel, and then you get this quantity. Okay. So this is Euler characteristic of sigma, and then so what is the Euler characteristic of genus G Riemann surface? 2G minus 2. I think it's opposite. 2 minus 2G. 2 minus 2G. So this is Gauss-Bonnet theorem. Yesterday I teach Gauss-Bonnet theorem, so it's a very timely topic. Okay. So this leads to, so therefore e to the minus s dilaton at low energy, what you will get is e to the minus phi 2 minus 2g. 2 minus 2g. So that's what you get from the dilaton action. So this is indeed will give you the interpretation e to the phi, e to the minus phi can be understood as string coupling constant in the following reason. So this motivates us, oh my goodness, I think I made a mistake. E to the phi, yeah, e to the phi is different. So that essentially this can be written g times 2g minus 2. G string coupling constant. So therefore, string coupling constant, I will explain why we can consider e to the phi can be the string coupling constant. E to the string coupling constant is just the expectation value of the dilaton field. So coupling constant somehow pops up from the worldsheet action. So the reason why, so it's a topological reason why it can be understood as the string coupling constant is that for instance, so for instance, if you consider the following, the 4-point amplitude, you always receive in whatever, so 4-point amplitude, you have G squared. Okay? Good coupling constant coming, so each vertex will give some coupling constant, right? So therefore, if you consider 4-point function, it should be G squared, and also same way. So same way we can have the whatever. This is again g to the cube. Okay, g to the cube. Let's look at Euler characteristic. So what are the three punctures? Do you know the Euler characteristic three punctures? This it's called pants. Anyway, Riemann surface has a pants decomposition, and this anyway maybe. Anyway, so what is the Euler characteristic of this guy? Do you know? Euler characteristic of this guy. Shall we do the computation? Let's see. So this is -1. Euler characteristic is -1. Can you see that? Well, what is the Euler characteristic of sphere? What is the Euler characteristic of sphere? 2. Okay, this is 2. Euler characteristic of sphere is 2, and you just get rid of 3 points. Okay, Euler characteristic is E minus vertex minus edge plus face, right? So get rid of 3 point means minus 3, right? 2 minus 3 is minus 1. Okay. So this is order characteristic minus 1. What is the order characteristic of the this guy? Minus 2. And so on. So we can do the, so you can just, how to say, pump up this Feynman diagram to the Riemann surface. What you would get is this is minus 3. Okay. So everything proportional up to sign to the G order of G unknowns. Okay. It's not Yamiz, sorry, G coupling constant G. So therefore, and in particular, so let's consider the following quantity. So if you consider this, how to say it, the bubble, so it only contributes to the vacuum energy, but if you consider this kind of stuff, so you have G square, right? Okay. What is the order characteristic of Riemann genus to Riemann surface? This is minus 2. Okay, 2 is just a minus 2. It's the same. So once you add this one, you just include one more, and then this is the fourth, and this is 4. Okay. So therefore, the exponent up here is minus of Euler characteristic, minus of Euler characteristic of the Riemann surface. So therefore, this diatom action naturally gives you interpretation of the vacuum excitation body of the scalar field. And if you just put it in the exponent, you get the coupling constant, string coupling constant. So therefore, somehow, the string theory have only one constant alpha prime, and the string amplitude coupling constant naturally pops out as an expectation value of diatom field. So one can naturally tune by just adjusting the vacuum excitation value of the diatom field. So that's why string theory likes the way we can explain the string coupling constant that appears. So it's just vacuum excitation value of diatom. Any questions so far? So now we are going to, can I erase this blackboard? So we are going to talk about the ghost field. So still keep talking about 2D CFD in string perspective. Where did I put my choke? Right here. So now we have the bosonic field, X, and then we talk about the free field 2D CFD, scalar field 2D CFD. And now we introduce some fermionic degrees of freedom, but not the physical fermionic one. It's just called ghost field. It's called BC ghost to fix some gauge of this. We have as I mentioned many times. So the action has the diffeomorphism invariant and also wall symmetry. So that if you do the path integral, you have to fix the gauge. And then to fix the gauge, we again use the Faddeev-Popov method and then introduce ghost field. And this ghost field turned out to be, again, will give you another CFD. So what we are going to do is as follows. Still doing the bosonic string, but we introduce the fermionic degrees of freedom to fix the gauge. And consider this BC ghost CFD. Okay. including bosonic and BC equals CFT, 2D CFT, and then we fix the gauge and again and move on to compute string amplitude. That's what we are going to do. So in the first lecture, we just introduced so-called light-cone gauge. So light-cone gauge, as I mentioned, light-cone gauge is you just fix x plus alpha prime p plus tau. So this is light-cone gauge to fix. So that the alpha plus n has to be 0, right? That's what we have. What we have done to fix the gauge. But this is manifestly not Lorentz invariant, because we fix some light ray plus direction and just impose this condition to fix the gauge. So it's not Lorentz invariant. And also, so we also see, so there's a Y anomaly in bosonic string when the worldsheet is curved. And then, so if you only consider bosonic string, so C is proportional is equal to D. C bosonic, C of X is just the central charge of the bosonic string will give you dimensional target. Do you remember why? Do you remember Cx equal to D? If you consider bosonic string, so this is 2D CFT, usual 2D CFT, free series, and this will give you central charge is equal to 1. Okay? And if you add dimension, D dimension, each dimension will give you central charge of 1, so it has to be D. Okay? So if you only consider bosonic string, free scalar theory is anomalous at the quantum level. And also, we need to do to compute amplitude. So we need to sum over G, and we need to do the integral over all the metric. So now in string theory, the worldsheet metrics dynamical variable, and also the x mu such that e to this string sigma model action x mu, and you just insert vertex operator. So again, so this amplitude enjoys the symmetry, so-called diffeomorphism, and also Weyl symmetry. So diffeomorphism is just physicist's way to write is just some coordinate transformation. Weyl symmetry just scale HAB by e to the phi HAB. So this is Weyl scaling. So it should enjoy the path integral also has this redundancy. Okay. So path integral has the redundancy. So these are not physical. This transformation will give you physically equivalent configuration in path integral once you perform diffeomorphism and Weyl symmetry. So you have to fix the case. Okay. The question is how to treat. So essentially, what you need to do is all metric space divided by Weyl group and diffeomorphism invariant. So that's what we need to do. In other words, so from here, physically inequivalent configuration. You need to pick physically inequivalent configuration. Weyl divided by diffeomorphism. This is exactly what you do in the Yang-Mills. all the space of connection divided by the gauge group. So one has to do the following integral for the Yang-Mills field. Okay, that's what you need to do. And then, so we do the same procedure. So to fix a gauge in Yang-Mills, we just use the Faraday-Popov method to fix a gauge. And we will do the same thing. To fix a gauge, so we will use the Popov method. And from to introduce the so-called and then introduce so-called ghost. Introduce ghost. And this ghost is also, this is called 2D CFT, so 2D BC, BC ghost CFT. It's a 2D BC ghost CFT. So ghost is Fermat degrees of freedom. So it's another kind of 2D CFT you will get. So if you include Bosonic 2D CFT, as I have written down here, and Fermat ghost CFT, it turns out that it's everything Lorentz invariant in target space, and then CX cancels C ghost, and it turns out that this CX times C ghost plus is equal to become 0. Once you tune D is equal to 26. Okay. D equal to 26. And then, yeah, so we original motivation is fix the gauge. So this problem is also cured. So everything cured this problem by introducing this BC ghost. So that's what we're going to learn from. Okay, so let's do step by step. So by using this one, so the metric can be just B 2 omega sigma. So this is wall symmetry. I think I should use omega instead of 2 omega. And then, so this is what you have learned in GR, how to transform the metric CD, AB. By using these two symmetry, one can bring H to H zeta. So this is wall scaling, and this is the just diffeomorphism. You get this one. So this configuration is a physically equivalent to this configuration. So therefore, we want to fix a gauge by introducing y is equal to, basic idea is very, very simple. But to perform this idea is very difficult. You have to do tedious computation, unfortunately. That's why one has to work hard as a physicist. So just include delta function. So 1 is equal to delta function times some measure with Jacobian. So this is Jacobian. So this is called Faraday-Popov determinant. This is Faraday-Popov determinant. And we just insert this 1 inside a path integral here. Okay. So essentially, what we are going to do is just let's call this one is. I think I call it delta. Yeah. So I call it this quantity as delta FP H hat. So h hat is some particular metric that is, so let me write down a schematic figure. So this is space of all metric. So it's an infinite dimensional metric, space of metric. So infinite dimensional space, but there is some orbit by symmetry of diffeomorphism Weyl symmetry that is characterized by this transformation. This is the orbit of the gauge transformation, and you have to pick some element, whatever element you want, whatever element that is h theta hat. So you have to pick some element in each orbit, one element in each orbit. That's what I hope. So to pick the metric at each orbit of gauge symmetry, so you just insert that function. The cost is just the determinant. Okay. And we want to compute this determinant by using Gauss field. That's the idea of the Faddeev-Popov. Unfortunately, Faddeev has passed away like a long time ago. Not a long time, 5 years ago or something. I already forgot. 4 or 5 years. He's the, oh yeah, there's one anecdote. Faddeev, do you know the Faddeev's first name? Faddeev. I know many Russian friends, so I heard him. Do you know Faddeev's first name? His first name is Ludwig. Ludwig. I forgot, there's a middle name of Faddeev. Huh?
It's not the Russian. No, it's not the German.
Yeah. Do you know the famous people whose name is Ludwig?
Wittgenstein.
Huh?
Wittgenstein.
Actually, Fadeev's father is also a mathematician, but he is also, when he was young, he learned piano. And he's a very, he was fond of the Beethoven. Beethoven's first name was Ludwig Beethoven. So he wants his son to be the composer and also composer and a musician, classical musician. That's why his father gives Ludwig to him, his name. And then his talent brings him to the pursuit of mathematics and physics. And he becomes composer. He's a director of this Steklov Institute in St. Petersburg in Russia. So he's a director a long time. So he becomes director of this Steklov Institute in St. Petersburg, and he produced lots of good, wonderful results. St. Petersburg, the Steklov Institute, there are lots of brilliant works and wonderful people show up. One of them is Reshtikin, and also Turaev and so on. And then somehow they are really good at the so-called integral models, quantum groups, and mathematical physics and so on. That's an anecdote. Yeah. So his father was a mathematician, and he really likes the music and also the music. That's why he gave the name Ludwig. Anyway, so that's an anecdote. Okay, so let's move on. So we just include this Faddeev-Popov determinant in path integral to fix the gauge. So now, since we introduce the, okay, so let's do step by step in that case. The H hat. I heard this story from Kashaev. Kashaev is the father of the volume conjecture. But Kashaev is also studying the mathematical physics from Faddeev. I mean, he's an expert for quantum dialogue. that are also 3D n equal to 2, 3. Anyway. Okay, so let's do step by step. HAB, Gn, dx, et minus string sigma model. And then we just insert 1. Okay, 1 is this one. So then to just put the C, H minus delta, H minus H hat, so C, and the for determinant. So if you perform the H integral, you only pick H hat no C, sorry, zeta. So at the end of the day, this is equal to Px for the fourth determinant of H hat e to the minus sigma s now only depends on H hat. So the metric is fixed. So you just pick one particular element in each orbit of gauge symmetry. Okay, so one remark. Remark 1, there's some residual gauge symmetry you cannot fix. For instance, if you do the conform transformation, you can cancel with Wahl transformation. Conform transformation, as I explained, conform transformation is the diffeomorphism in such that this metric is e to the some factor, whatever, e to the some factor h. That's the diffeomorphism that leads to this symmetry. So that factor cancel with Wahl transformation. So therefore there's a residual gauge symmetry. And also, so this will be fixed carefully next section. Okay, next section. So this will be will be done in next section or next lecture. 2, and then also there's so-called. So if you consider this object DHAB Gn divided by Y times diffeomorphism. So this is actually called so-called modular space or Riemann surface. It's complex. I mean, it's equivalent to the modular space of a Riemann surface. Riemann surface. I will explain what is a modular space it is. People keep asking what is a modular space? What is a modular space when you learn string theory and so on. So in the differential geometry course, I would teach modular space some in future in differential, not string theory. I think it's a good. I also briefly explain what's a modular space or Riemann surface in the in this lecture too. But more basic pedagogical introduction, we'll give a lecture on the differential geometry course. Anyway, it's recorded. But if you're interested, you can come. I will tell you when I teach the modular space. I mean, it's a very deep subject, but you can introduce modular space very pedagogical way. For instance, modular space of, for instance, triangle, similar triangle. I will introduce this basic notion of the modular space triangle. Next is the modular space of Taurus. You might have heard of it. So modular space of Taurus. So for instance, this is one Riemann surface that can identify by just identify this square with the opposite side of edge is identified. You get torus. And then once you fix, so the modular space of Riemann surface actually the space of the, roughly speaking, space of the shape of the Riemann surface. So in the case of the torus, once you fix with the complex plane, you can take tau as the, so you can fix, so this is the imaginary axis, this is the real axis, and you just fix one edge as 1. And tau can vary. If you vary tau, the shape of the torus will change. Okay. So of course I just identify the opposite edges. Okay. And tau can, once you change tau, the shape of torus will change. Okay. But there's some so-called this tau, the position of this edge is called, the space is called Teichmüller space. And there is a so-called residual global symmetry that acts on when A, B, C, D are SL2Z. And then there's a tau goes to A tau plus B, C tau plus D. Okay? For instance, if you change this is equal T transformation, you can change tau goes to tau plus 1. That doesn't change the shape of the torus. I mean, bring this patch into here, you get the original one. Okay. So this is T transformation of tau plus 1. Another is hard to imagine, but how to draw actually. But it's easy to imagine. Tau goes to minus 1 over tau. That is also does not change the shape of the. That's called S transformation. And this is called T transformation. And this S and T will form this is called SL2Z. And this SL2Z does not change the shape of the torus. So therefore, Teichmüller space is the upper half plane. Teichmüller space of the torus is the upper half plane. But you have the quotient upper half plane mod SL2Z. And precisely speaking, minus 1, 1 does not change anything. Yeah. So once you put it, minus 1, 0, 0 does not change anything here. Right? Minus 1 cancel. So essentially, you have to get rid of minus 1, identify 1 and minus 1. That's called projective SL2Z. This equivalence process identify 1 and minus 1 element. And the quotient, that is the so-called modular space of the Riemann surface. And of torus. I mean, these are fundamental concepts. Unfortunately, I mean, Gauss has already noticed this modular space back in 80s. Back in 80s, 19th century, and in fact, so this is upper half line, and then these are you. Okay, some of you guys take a differential geometry course. These are geodesics of the. Anyway, upper half plane with metric dx square plus dy square divided by y square. So you already know. And then T transformation, just map this, how to say. So this domain is mapped to T, and S transformation map this domain to here. Okay? Do you understand what I mean? So this domain is mapped to this domain by S transformation. So this is geodesic. S transformation map this geodesic to this circle. Indeed, maybe this circle. Sorry. And this geodesic is transform this circle. And this S transformation map this upper half plane, this domain in the upper half plane to this region. This one just shift. Okay. And then this is called fundamental domain. So this is called fundamental domain, or this is indeed modular space of Riemann surface is genus equal to 1. And precisely speaking, you have to be careful about edges. So edges, you have to, only this part is essential in the edges. If you do the T and S transformation, this yellow part identify the opposite edges. You need to include only yellow part, but not the other part, white part of the edges. So this is called modulus of Riemann surface, and this figure is already drawn in the Gauss's collector paper, without mentioning anything. He already noticed, so Gauss is a genius. And then there's another genius show up in 19th century, so-called Riemann. So he already noticed so this is genus G Riemann, genus 1 Riemann surface, and he already noticed modular space of genus G is the R6G minus 6 divided by mapping cross group action. So 6G minus 6 is the is tachymeral space, the same as the space of this tau. Okay. But there is a global symmetry called, in this mapping cross group of the torus is just SL2Z. But for Riemann surface, you have to group so-called, you have to do the Pantz decomposition. Anyway, it's very deep subject. I mean, personally, I'm very interested in this subject. Exactly the place mathematics and physics intersect. So you do the Pantz decomposition. Okay, so if you cut along yellow line, oh my goodness, I think I should put something. I made a mistake. Where did I make a mistake? Question is, yeah, so I don't need this one. And also I don't need this one. So, if you cut along yellow line, which each piece is just a Pantz. Okay. And then, so you have to form the Riemann surface, you have to group along yellow line. Okay. And but there's a so-called symmetry that actually rotate 2 pi. Okay. Once you can rotate 2 pi along yellow surface when you group, that will give you, that doesn't change. Riemann surface, that's called Dent Twist. It's called Dent Twist. So in other words, if you have a line like this way in a Riemann surface, but if you do the Dent Twist along this yellow line, what you get is come back like this way. Okay, so that's called Dent Twist. That is create so-called mapping cross group. That group that is a symmetry of this tachymeral space. If you mod this is discrete group by tachymeral space divided by this mapping cross group, you get a so-called the modulus of the Riemann surface. And then Riemann already noticed the modular space is 6G minus 6, but he doesn't have so much intuition about the global structure of this modular space of Riemann surface. But anyway, so this is the exactly what's going to happen in the modular space of Riemann surface. For puncture, you can include puncture and puncture and G. So this is a dimension of this modular space of Riemann surface is equal to, and the dimension R is 6G minus 6 plus Cn. Oh, sorry, 2n. So, in fact, at the end of the day, so if you mod out the Wahl and Wahl symmetry and the diffeomorphism symmetry, from the metric space, at the end of the day, so you have to reduce to the finite dimensional configuration. So this is module space of Riemann surface. To compute string amplitude, indeed, one has to string amplitude reduce integral over this module space of Riemann surface. So at the end of the day, so in string theory, string amplitude. So even though I already here erased the metric dependence, but at the end of the day, needs an integral over the module space of Riemann surface. So it's a finite dimensional integral, but I just omit this subtle detail. Just for time being, let's forget about it. For time being, so next lecture or next section, I will introduce the module space of Riemann surface. So these are two subtle issues. They are related, actually. They are related. So, but for me, just keep it. Just keep this remark in mind and move on. I think it's a good time to stop, take a break. After break, I will try to deal with this determinant by introducing further Popov course, BC course. Let's take a 10-minute break. So, if you have done homework, just send it now. And also, I just graded your homework here, so you can just take. Ladies, you can open the next. Can you open? You cannot? You can? So is this your submission?
就是你每次取一个 x 一个 x， 对吧？取完之后再放个基础，对，它就只说这个东西，你就基本就只看个形式而已。你别用这个颜色做的话，可能你如果做这个，
但是它不是接都是负吗？没有好点。他妈就我一想就是他妈我就写上去。
你只看它的话，它根本没有 W 的部分，它只有 K。
这个积分的是那个呀，这个 O W 积分里面的。你说变分以后，它其实这个当中是给出根号。
就是实际上你，它每次约需要你一个新的加 W 约在一起，你只看 X K。我自己的话，它约不出东西。
这个是那个，就这个东西它是积分里面的，它后面当然没有关系。就这个是它那个，就这个色，这个是草。也没来过。X 做的它直接 Z prime 这个 Z 和它积分里面是是。
但是你最后这个，它其实这么写，最后一个多的是可以是规范的，就是你最后球赛应该是很复杂的，但是这种东西，就是你实际上球用于之后，你还会，你要求 P 的时候，你最终这项里面还是有摸的项目，你就把这样的摸也停下来，只有多一部分的 P 还有多的。你就觉得喜欢的职业整个的三场，那结果呢也算是，对你球批没有直接帮助，对吧？反正你球只是约项而已，还有多么多的元方的这种。
不需要我球批啊。这都是说这个，教练是让我球批，他是非有的。
他就是球批，
不是。你想 OP， 他是不是 field 有两个不是，这不是他们要说原始，而且做那个东西是 OP 展开不像人去刷出一个 primary field。
他为什么给这个？
但是他还给我底，他还给我底。
他是自己最喜欢的。
差不多对。
他这个写出来基本就是这个，就是你把 X E M W 拉下来写出来，这样子一个复杂的。我知道他
就这个定义啊，就自
己上下的定义都不是很清楚。
就是你用这个算出来，这个 为什么内向的人说的 private field 要是等价呢？
Still something like so even if you don't get it, it goes to my secretary. So when secretary is daughter.
是造成的对你有个作用，对这个我还可以。
Okay, so shall we start? Resume. So now let's treat this 44 determinant. So today's homework is about BC ghost. So at least I mean BC ghost. So where was the choke? Oh, yeah. So let's treat for the Popo ghost. To treat for the Popo, so let's first determine what is the explicit form of this determinant. To do that, so we just start with, oh, I already erased. Stupidly erased, and then so here. Okay, so this is exactly the transformation rule. And let's look at the infinitesimal version of this transformation. Let's go h hat. So delta h hat AB is just an infinitesimal version of this transformation. So this is the infinitesimal version. So this first term comes from vowel symmetry. The second term comes from the conformal transformation, not conformal diffeomorphism. Anyway, if this is zero, anyway, it's becomes conformal vector and so on. But anyway, so this and define the following. So where the P AB is delta A, not delta, nabla B, epsilon A, HAB, and nabla dot epsilon, and then omega is just scalable for this part. The reason why I did this such a scaling is you will see as follows. So therefore, so this is the explicit form of infinitesimal version of the transformation, and this for the important determinant is determinant of delta P dot E omega tilde divided by delta B omega. This is determinant. Okay, so then what you get is the matrix roughly the form of theta B0. When you take the variation with respect to epsilon, you get the P, but variation with omega, you don't see anything. Or on the other hand, if you do the variation of epsilon, you get something, but then you get the 1 here. Okay. So this is to do the determinant. This is determinant of P. So essentially, what we are going to look at this P piece. And then, so we will follow usual method of pop-up. So yeah, usual way of the so if you take QFT2 in my course, I already explained. So this is finite dimensional version of the this is finite dimensional version. And we will use infinite dimensional version of this one. So therefore, determinant delta of P is the infinite dimension. You just use so this psi and theta is Grassmann variable. It's a Fermat variable. Okay, Fermat variable. So therefore, we introduce two Fermat field B and C. These are Fermat, and put the pi is first sigma chat PAB P dot C B. Okay, so that's the what you would do. So in other words, so you just sign theta correspond B and C, and this summation becomes just ordinary integral over the two-dimensional Riemann surface. And then we want to have the determinant of this matrix N, determinant P, you just sandwich by B and C. Okay? So that's the infinite dimensional version of this simple Gaussian integral, Gaussian type integral, with using Grassmann variable. Okay, so that's the, and then we treat, so this is path integral, so we treat as some dynamical degrees of freedom physics, but it's ghost, so it's called BC ghost, and then we just define dp dc, and this quantity as the I as ghost p, and then sigma ghost S ghost is 1/2 pi b squared sigma BAB delta CP. Now I just take BAB is a Grassmann Fermat degrees of freedom, but AB is symmetric traceless. So anti-commuting Fermat degrees are symmetric and traceless. And C is just a vector. CA is just vector. Okay, so that's how you introduce the Fourier ghost to fix the gauge. Okay, so that's, then we will consider the following thing. So now, so we have, so in total, what we will consider is as follows. So Z of H. So there is a remark, but I wrote in lecture note a remark, but I will come back to this point in later, so I'm going to skip. So there is 3 dynamical degrees of freedom. Okay, X is free boson, and B and C are ghost Fermat degrees of freedom, and then we have. It depends on. Okay, sorry. I think I'm already going to the. Okay, so let's go into the Euclidean signature. So x h hat by using weak rotation ghost, and this is b c h hat. Okay, so we are going to consider such a 2D CFT. Now it's manifestly Lorentz invariant, and then we would like to consider 2D CFT. So 2D CFT, one of the most important concepts is central charge. We already know central charge of this guy, so we need to compute the central charge of this guy by using this action. Okay. I think I missed some remark about the why this symmetrical traceless. So indeed, so the reason why I just bring this into this form, this is also symmetric traceless. This is symmetric. Symmetric traceless. So therefore, so when you do the Faddeev determinant, Popov determinant, you just sandwich by the symmetric traceless, and this it's related to conformal killing vector. Conformal killing vector is just a p dot Gibson equal to 0 is conformal killing vector. Anyway, so that's the reason why you get a symmetric traceless condition from the 4B field. Okay, so now we fix a gauge. So we just pick particular metric for Riemann surface, and then we manifest the Lorentz invariant. And then let's see. So therefore, the two problems I raised at the beginning of this section has been solved. And what is it? How about the central charge issue? This wire anomaly issue. So S ghost is, so just rewrite this action more explicit way in okay, so for H hat, so we can take some particular gauge, so I will just take the conformal gauge. So as I mentioned, you can always put the metric as H hat as, okay, ds squared is dz and then dz bar. This is called conformal gauge. So by using worldsheet diffeomorphism, you can always bring the metric of the worldsheet as the locally the just conformally plot. So that's called conformal gauge. And I think did I make a mistake in the difference? It's okay. I think I made a okay. I think yeah, update elections it should be okay. I put the 2 here. Sorry, 2 here. I think I should use C and C find in this. So as a H hat, so component as a H hat. So you can pick particular metric for worldsheet. I just pick this conformal plot metric. Then this S ghost can be written as follows. So this is good exercise, and this is related to your homework today. Nabla C, C bar. So you can easily bring this action written here into this form. This is good exercise, so I'm not gonna do that. And this one is also 2 pi is per Z, and then since we already know Christopher symbol is only non-vanishing, only for this guy. This is, I really forgot what's the answer. 2 omega, the omega, and also the same quantity. So remember, this is the only non-zero, non-trivial element in Christopher symbol. So therefore, if you use this fact, one can just derive. This is a good exercise to derive this action by yourself. It's a good exercise. Maybe I asked, I already forgot how the homework is, but maybe I asked it already. Homework 4. And I call this, I call B is BZZ, and the B bar is, I mean, usual way to define this is C bar equals CC bar. Then the equation motion is just, this can be written, if you introduce this variable, the action is written by, it's just a very simple form. Okay, so this is the action of the BC ghost. So there's a holomorphic sector and the anti-holomorphic sector, and the B and C are parametric variables. Okay. So the Polchinski section 2 only consider left-moving holomorphic sector. But to fix the gauge, you need to introduce both. And the Polchinski, as far as I'm sorry, I've become rusty already. Section 4, he talks about section 3 and section 4. He talks about this BC ghost. I mean, yeah, the BC ghost part in Polchinski is for me, it's written. And one thing I can remind you that the Polchinski is not easy book to read, but Appendix B is very nice. So eventually we will go to superstring and target space, but Appendix B is a must read. So anyway, some part of the Polchinski I really like. Some part for me it's a bit difficult to understand. So you have to consult some book. I have to consult some book and then paper and so on. Anyway, that's how you need to study string theory by yourself. So this is the action for BC ghost, and then we will do the we will take the equation motion. So therefore, so equation motion for this sector is this one. So therefore, B and C are homomorphic object. Okay, homomorphic object. That's I call homomorphic sector, and this is from here. Oh my goodness. So this is anti-homomorphic. Equation motion tells us the second one is anti-homomorphic. Okay, anti-homomorphic sector. And then, so we will do the same thing. So in the homework, you just do the free Riemann computation. We will do the same thing. We just define what is a T, what is what kind of primary field is always given a CFT. Given a CFT, this is 2D CFT. What is this? First question, what is it? How do you write the stress energy tensor? And what are the primary fields? And what is the central charge? And it's also OP. So that's what we're going to ask. Okay, to do that, we do the same thing as the free bosons. First, you just insert. I just only focus on homomorphic sector from now. So we just do the same thing as the free bosons. You just consider the path integral, and you take the variation with respect to B with insertion of the B field of W. then what you get is the usual thing, e to the s ghost minus 2 pi delta c of c. So this first b acts on here, and you bring delta bar c into here, okay? And then you multiply b here, bw. Okay. So that's the first contribution. The second contribution, just delta b acts on this b field, okay? This b field, and then not capital B, small b field goes to b field, and you get delta function, okay? I mean, this is what we have done even in free bosons, okay? We have done the same thing. We just insert x and with, how to say, take variation with respect to x, and then you get this one, right? I mean, okay, do you remember what's this? What's this? Singular contribution. Without looking at lecture notes, can you tell what this is? Good. Log z minus w. That's what we have obtained. We want to have similar thing even this BC ghost. That's what we are doing. So to get this relation, we do exactly the same thing, right? Do you remember? We need to do the same thing. Okay, and then so to get this one, again we use this one, right? Do you remember? Oh my goodness. 1 over z squared. Oh my goodness. I myself forget. And this is delta z. Z squared. Sorry, I need to look at the lecture notes. Sorry, I myself forget. I cannot blame you. What was the answer? I have a very poor, oh my goodness, yeah. I have a very poor memory. Yeah. And I think there is something here. 2 pi or something? Yeah, 2 pi. So we use this fact, delta z, to get this relation. Do you remember? To get this one. Okay. We do the same thing. So delta is, you can use this one, and then the holomorphic one. So you have to be careful. So yeah. So anyway, so this kind of computation you have to be fluent when you study 2D CFT. Even whatever point of view, once you do the OP computation, even condensed matter and so on, you have to do the OP computation. So from here, so this operator formalism, this has to be equal to 0, which means this. Okay. And similarly, we can take the same thing for del C, and then what you would get is easy. You can just swap B and C. Okay. What I'm doing here? Sorry. C and this is B. You should correct me. So that's what you get by taking del C. Okay, that's easy to. It's easy to derive. Then again, we will use this relation. So then once you apply holomorphic derivative, what you get is now del bar 1 over z has to be 2 pi delta function. Okay, So you just apply, you just compare both, and then see what's going to happen. So compare both, and then what you can easily tell that the B of C, CW is equal to 1 over is C minus W, and then CW and BC is 1 over, oh my goodness, why are they right there? You should correct me. W minus C. Okay. Do you understand the logic? Okay, you understand logic. So as you can easily see, so if you swap B and C, you get the minus sign. Yeah? So therefore it means if you swap B and C, you get the minus sign. So therefore it's the Grassmann parametric variable. And the difference is also, you can see this is the, I mean, you can easily see compound dimension, right? You can easily guess. I mean, is what? Do you remember? What is the exponent here? Do you remember? Huh? What was the exponent? So this OPE, what was the exponent here? Square, good. The reason why I get square is compound dimension, this guy is 1. Okay? Yeah. Anyway, compound dimension 1 plus 1, you get 2. So therefore, you can easily guess what is the compound dimension. But anyway, so that's eventually what we are going to see. But that's not the case in the. That's not the case in here actually. So that's not the case in here. So this one is 1 over C minus W as you did in the homework. Since sign are the same, share the same compound dimension, you get the 1 half, and you get the 1. But in this case, a bit different. BC goes a bit more complicated, and we will see. Okay. So. So let's determine this guy. The most important is stress energy tensor. So from here, sorry, I just tell you it's a bit slightly misleading. H is equal to 1 for this guy, and this is psi H is 1 half, because 1 half we get 1, but a bit here a bit different. To see that, we want to see the method. Yeah, the reason why is that the here I already erased. Did I erase? I think I erased. So originally this is the how to say symmetric tracer 2 tensor. It's a 2 tensor. This is vector. That's why it's a bit different. So BAB. So this is symmetric traceless tensor, and the CA is just vector. So therefore, under the compound transformation, so what you can do now under cross. So it's so this is the 2 times C, and the delta C is equal to delta minus delta C. So the reason why you get the minus sign is that where did I define the BC? Oh, did I? Oh yeah. So here you have a downstairs, index is downstairs, two indices downstairs. That's why you get plus 2 here. It's 2 tensor. It's a, how to say, symmetric, so that's why you get 2 by compound transformation. On the other hand, here you have an upper script. Okay, so therefore minus sign you get. Okay, so that's a conformal dimension. So that's why. So therefore, so this is under conformal transformation. You can just derive this by usual method. I mean usual like how to say BAB is equal to. I mean if you use this method. I mean sorry. I mean, if you want to check this one, so you just use this ordinary way, CD, B, CD, okay? And then plug the conformal transformation into here. What you will get is this guy, 2 times this one. And then, on the other hand, if you the upper script, you get you have to swap tilde and sigma, right? So you get on the other hand, A is, tilde is upstairs. And then without tilde is downstairs. Okay, so therefore you get the opposite sign minus, and only 1. That's the difference. How you get. Okay, so therefore the conformal dimension of B is, as you can see, 2, and the conformal dimension of C is minus 1. And they count there, you get the 1. Okay, do you understand what I mean? X1 and 1. Hopefully. Okay. So to get this answer, it's easy. As a physicist, always easy to. Is it good at? Has to be guess. I mean, it's easy to guess the form of stress energy tensor with this information. So we know this OP of B and C, and also we know the conformal dimension, how they are transformed the conformal transformation. So therefore, T ghost. I mean, this is. I mean, this is a bit. Anyway, I mean, this is. So this is the answer. This minus 2 really come from this 2 here, and plus 1 really come from here. And if you do the OP with the T ghost, TW, what you will get is conformal dimension of BW C minus W square plus and T ghost, and this one indeed can be obtained from action. So as you notice, TAB is some proportional to del S del HAB. So you start with the original action, take variation with symmetric, you can get this one, indeed. You no need to guess, actually. And the ghost of Z and CW, if you use this, the OPE between C and B, you get minus 1 BW. Let's go. So CW. CW Z minus W square plus. So this is the indeed the primary field. The primary field. So therefore, B and C. So HB is equal to 2, HC is equal to minus 1. They are both primary field. Okay, and then, so it's a super tedious exercise. Yeah, 1 half. But, okay, I have enough time. I think this is homework to do. So to compute central charge, you have to compute TT OPE, and then this is the exercise. It's super tedious. I will remind you, you have to, if you want to do the homework, you have to do by Ali. I mean, it's very tedious. It's straightforward but tedious. Okay, so this is the how you get the OPE. So therefore, C left is equal to C left, and also the same piece coming from C right, or holomorphic, anti-holomorphic, minus 13. So therefore, C ghost is equal to minus 26. So therefore, in order for the total central charge to vanish, if only if again you get the same target dimension, d equal 26. Okay. So therefore, you have a question?
Well, I'm just confused. So from conformal invariance, if two-point collision function is not zero, the two fields should have the same conformal weight, but why is not true here?
It's ghost. That's one of the reasons. And also one is two. That's one coming from two symmetric tensor. The other is coming from vector. That's one of the reasons.
So I think from the fact that they are primary fields, we can deduce that they should have the same conformal weight, just like in the third homework. So I'm not sure where it goes wrong.
I don't understand your question. I mean, for instance, here you have opposite conformal dimension, right? So if you act derivative delta acts on C, you have an opposite conformal dimension. One is -2, one is 2, and you get the delta function. That's consistent, right? So which means C has to be -1. Do you understand what I mean?
I think in the third homework, from the conformal invariance, mean one way you transform D to -1 over D, and deduce that the two fields should have the same conformal weight.
Oh, so you mean 2-point function when you consider OP phi1 of Z1, phi2 and Z2 is equal to C12, Z1 minus C2, H1 plus H2, and delta H1, H2. That's what you mean. Okay, so therefore, of course, that's true. That's definitely true. But 2-point function, this is different from 2-point function. It's an OPE. OP is different from 2-point function. So that means if you consider this object, it's a ghost field, so it doesn't mean anything. It's a ghost field. You cannot consider 2-point function. It's not physical quantity. Do you understand? So this does not mean anything. It's no physical operator.
But in mathematics, is there anything wrong?
So for this one should be 0. Should be 0 if you consider.
But the BOE is 1 over Z minus.
The OPE you mean? OPE?
Yeah, B.
Okay.
Z.
This one?
Z.
This one?
I mean, in the third line,
This one?
Yeah, that.
And take this the expectation value, and then you get the something 1 over Z. You mean?
Yeah.
That's true, but oh, I see. Okay. Actually, that's a good point, and we will come back to that point that the yeah. So this vacuum has to be physical vacuum, and so we will introduce Vrc symmetry from now, and then the vacuum has to be BRC invariant, and then therefore, so if you consider BC ghost, you get 0. That's coming from BRC, the physical condition. Any other questions? Okay, so we talk about BC goes to the CFD. Yeah, so you have to prepare a little bit. This computation studies. Okay. So again, the computing central charge. So if d is equal to 26, free from so therefore we just get rid of we just solve 3 points with IRIs, so Lorentz invariance and also Y anomaly and also gauge fixing have been done by introducing BC ghost field. Okay. So as he pointed out, so you have to be careful with once you introduce ghost field, you have to be careful about which state is a physical, which state is not physical. To do that, I mean, we also have the same thing in YAML. So ghost field will lead to so-called VRC symmetry. So VRC charge, so VRC, I call B. VRC charge is the natural charge of this symmetry. Natural charge of this symmetry, and that actually, this natural charge of this symmetry is nilpotent. It's called nilpotent. So it's the same as the differential geometry. Dynamical homology, when you run dynamical homology, d squared is equal to 0. Okay. So it's very basic relation coming from physics. Somehow corresponds to basic relation, basic equation, whatever, of the x derivative square equal to 0. So it's a dynamical homology. So. And the physical quantity should be annihilated by, so physical state, the condition of physical state has to be annihilated by the VRC charges. So on the other hand, so here even this dynamical homology, when you learn dynamical homology, so you have the dynamical homology defined by manifold M of R. Dynamical homology is zk divided by bk. I mean, so zk is a closed form. Zk is the omega in omega k such that the omega equals to 0. It's closed. It's called closed form. And the pk is the exact form. Is a d lambda such that lambda is omega k minus 1. So it's an exact form. So it's the same. So if you have f is dA, but there's a gauge symmetry, A can always add A plus d lambda, right? So f is always closed form. But there is a gauge redundancy, d lambda is exact form. Okay? So you just quotient by A can be, so this, yeah. Anyway, you understand what I mean. So you understand, so When you consider dynamical homology, when you use d squared equals 0, you just have a cross divided by exact form. So we do the same thing for BRC symmetry. So if you have consider this one is the same, if psi is related by exact form. Okay. So physical is the same. So we just identify. So the physical is same. Same configuration. So therefore, the Hilbert space of physical Hilbert space is indeed cubical homology. Is cubical homology. Which means the H QB closed divided by H QB exact. So it's the same way to define a dynamical homology. I'm not sure if I include this one, but so indeed, so the actions S sigma plus S ghost, which should I write down? I think I should write down as 2 pi d square partial x partial del x plus b del c plus b bar del c. So this is the action you will have. I'm not sure, to be honest, is there 2 here or not? The question is, I already forgot. Can you take a look at Polchinski? Check whether they have this action. I already forgot that maybe some question mark. I'm not careful about this. This action has a BRC symmetry, which that the x. So this to check this one is also very tedious. I'm not sure. Did I include this one in the homework? When I was a student, I tried to check this BRC symmetry, and it took more than 1 day, as far as I remember. Yeah. Anyway, the ghost and the holomorphic one. Holomorphic one is the same. So it's called Vrc transformation. So this action enjoy this transformation. So, and did you check how? Okay. So this is it. So you can check by yourself, but it's very tedious computation one has to do. It's same as like a supersymmetry. So the one thing you have to notice that once you apply this delta x, you get some permanent quantity. Okay. In addition, so it's a permanent quantity. Permanent times boson is permanent quantity. And if you apply BRC on permanent quantity, you get a bosonic. So permanent times permanent is bosonic. Here also bosonic quantity. Okay? So it's like it's a relation between boson and fermion. Okay, it's more like so even supersymmetry you have a similar relation. Okay, and then yeah, these are super tedious exercises one has to do. And in fact, I think Nessa current of this symmetry is given by as follows. JB is CTX of C plus 1/2 W dot C of Z T ghost of Z and plus 3/2. Okay. So this is Nessa current, a homomorphic one. And if you do that, let's see. The OPE of these current, yeah. So for instance, OPE of JB of Z and B of W. If you do it like this way, you get the quantity coming around here. So for instance, coming here, so you get, I think what you would get is T of X plus T of G H divided by, I'm not sure I or some number times Z minus W, and so on. So that's, you can compute by using the OP between B and C. Okay, so that's an exercise to do. Did I include in homework? I already forgot what in the anyway, so I can check later maybe. I think yeah, one has to do this homework by itself. It's okay, and so on. So last 10 minutes, I just explained how the physical state is constructed. So QB, so Nessa current, this Nessa charge is just a circle integral, spatial integral of Nessa current here, and this including the how to say, if you do the model expansion of B field, so this plus 2 really comes from conformal dimension, and the C of Z is also do the model expansion in similar way. Cm Z m minus 1. So this minus 1 really comes from the conformal dimension, and it just do the same. Do the plug this one into here and perform the contour integral. And then at the end of the day, what you will get is the so what you get is QB is equal to Cn L minus n x minus delta n 0 plus sum of m minus n over 2 Cm Cn e minus m minus n and normal order. So that's the expression for QB by normal QB, the Vrc charge. But in terms of this generator, in the mode of B and C, and then the bosonic mode. So the first part, as you can easily see, the first part coming from this one. Okay. And then if you combine them together, you get the second part. It's very tedious exercise to get this one. So as I mentioned, so we need to impose the reason why I did this model expansion. Just write down the QB is as a mode is since we need to impose the physical state as a QB cohomology. QB cohomology. It's annihilated by QB. Okay. So So in previous bosonic case, this is a vacuum state. Okay. So this once you act on P mu, you get K mu. So this is vacuum state. Okay. But now, so we have a B and C. Okay, B and C. Now, so after the ghost, BC ghost, including BC ghost, you have a two-spin system you have to include due to the presence of the Fermat degrees of freedom B and C. So ghost generated two state spin coming from the zero mode. I'm not sure if I can reach today. So the ghost generated two-state spin. So therefore, you have in my lecture note, I just write down K plus K and down. So the ghost system is this. Fermat degrees of freedom. So you create the two-spin system, and then usually we can just impose the following condition. This acts on so if n is greater than 0, acting on spin up state, you get 0. And the same thing, if you b less than 0 acts on the spin down state, you get 0. Okay? And a similar condition for C, you can impose. So one can impose this condition to be a spin system, Fermat degrees of freedom. However, one has to be careful. The same for C, B and C, the same. Oh my goodness, I made a mistake. Sorry. So this is plus. Sorry, all plus. Sorry, all plus. This is annihilate. Sorry, these are yeah. So creation and annihilation operator. So n greater than both has to annihilate by positive mode, but one has to be careful about the zero mode. So since zero mode satisfies the following function, since it's the Fermat, the square equals 0, of course, but the B0 and BC, C0 equal to 1, that's coming from this OPE condition. B, C, CW is 1 over C minus W. So that's the BC and C minus W. So this, if you do use this OPE condition and only look at the zero mode, you will get this condition. And then, so therefore, one has to be careful about the zero mode. And then, to get the right physical spectrum, what you will need to do is impose the following condition. So the zero mode, so B0, so the gauge we impose is this equals 0. So among physical state, this has to be 0. This is a condition, sometimes called Ziegler condition. Okay, so therefore, indeed, so this will give you the condition that B0 acting on this one equal to 0, and C0 acting on 0, and B0 acting on this one is equal to negative. C0 acting on this condition is positive. Okay. So that's what you get from this condition. So these conditions. So as you can easily see, once you act B0 twice, you get 0. As you act C0 twice, you get the 0. And once you act B0, for instance, and C0, act on, let's see, like this way, you get 1. You should get 1. Shall we take a look at it? The B0, C0, plus C0, B0, and this one is 0, and then this one brings up and down, and you get the 1. Okay? And also similar thing can be done for this one. If you impose this condition, you get also 1. So this physical Ziegler condition, just pick this one as a, let's see, which one is a physical condition? Up state is, yeah. So the ghost vacuum is this down one. So B0 analyzes the down spin. So this one is ghost state, and this is true vacuum. So that's what the, sorry, I think I made a wrong statement. I'm sorry, I think I made a wrong statement. So sorry. So B0 physical vacuum has to be 0. So therefore, the vacuum has to be, how to say, the downspin. So this one is true vacuum, and this is more, this is vacuum, and this is some excited state you can consider as. Sorry, I think I made you confused. So, let's see. I think next lecture, I think it's almost time, so next lecture I will briefly review this part, next time lecture. So upshot is that so physical states QB is equal to 0. But since due to the thermic nature of the BC ghost, you have anti-commutation relation between B and C. So therefore, one has to introduce two spin up and down states, and the question is which one is vacuum. And if you impose this condition, indeed the down one is the down spin is the true vacuum, and this can be understood as the some excited states. Okay, so that's the condition we impose. And then we will see what's going to happen, what's the physical spectrum and so on in D equal 26 dimension. That's next lecture's topic. So I think this time I did a poor job, so next time at the beginning of lecture I will review more in detail about BRC quantization. Okay, let's stop here. So if you have questions, just tell me.